Roman carpenters built an empire using wood alone. This mastery of ancient Roman carpentry created structures that have withstood millennia, and their most astonishing secret was constructing entire buildings without a single nail. By the end of this journey, you will know the hidden techniques that gave Roman woodwork its legendary strength. How did they join massive timbers so perfectly, and what mysterious preservatives kept their wood from rotting for centuries? What does it take to build something truly meant to last? The true genius of Roman carpentry was forged in the tools they wielded. Instruments of such refined design, they became extensions of the carpenter's own hands. Far from relying on simple hammers and saws, they employed a specialized arsenal. The adze was a master of shaping, a curved blade on a handle used to skillfully hollow and sculpt massive timbers into precisely curved beams for ships and roofs. Then came the bow drill, a simple yet brilliant device. By winding its cord around a shaft and moving the bow back and forth, a carpenter could achieve a steady, rapid rotation, boring clean, consistent holes for their complex joints with a level of precision that was, for its time, remarkable. But perhaps their most revolutionary innovation was the Roman plane. Unlike earlier tools that merely scraped the wood, this plane featured an iron blade, called an iron, held securely in a wooden body at a precise angle. This allowed a carpenter to shave off thin, controlled curls of wood, creating surfaces so flawlessly smooth they often needed no further finishing. This was not crude work. It was the birth of fine woodworking on an industrial scale. And this leads to a surprising discovery that changed our understanding of their capabilities. We once thought of ancient woodworkers as primarily using stone and bronze, but Roman carpenters had access to high-quality iron and even steel. They created tools with hardened metal edges that could be sharpened to a razor's keenness. This gave them unprecedented cutting power and durability, allowing them to work faster and with greater accuracy than anyone had previously thought possible. These were not primitive implements. They were the secret weapons that built an empire, one perfectly planed board at a time. That arsenal of razor-sharp tools was put to its ultimate purpose in the joints. Roman carpenters were master architects of wood, creating intricate, interlocking puzzles that bore immense weight without metal fasteners. The most fundamental of these was the mortise and tenon, a joint of elegant simplicity and brute strength. The tenon is a protruding tongue of wood, carved perfectly to fit into a matching slot, the mortise, on another beam. But this was no simple peg in a hole. Roman craftsmen would shape these joints with such incredible precision that when hammered together, the wood fibers would compress and grip, forming a bond often stronger than the surrounding timber. You can find this same principle in the wooden chairs of today, but the Romans scaled it to monumental proportions, using it to frame everything from humble market stalls to the sprawling roofs of basilicas. Yet for their most prized possessions, they employed an even more cunning technique, the dovetail. This joint, shaped like a dove's spreading tail, locks together in a way that resists being pulled apart. Roman craftsmen would hide these joints within the corners of their finest chests and furniture, a secret signature of quality known only to the maker and the owner. It was a joint that declared the contents within were valuable, protected by a wooden puzzle that would only grow tighter under strain. But for truly massive constructions, like the supports for an aqueduct or the framework of a massive ship, they turned to the lap joint. This was the genius of shared burden. Instead of simply butting two beams together, carpenters would carve away half the thickness from the end of each, then overlap them. This created a broad, flat surface for glue or a wooden peg to secure, distributing the immense forces of weight and movement across a much larger area. It was a lesson in structural empathy, understanding that wood works best when stress is shared. How did they achieve such flawless fits on a scale of tons? The answer lies not just in their skill, but in a hidden world of measurement and layout, a system of precision that governed every cut. But the most perfectly fitted joint is useless if the wood itself decays. Roman carpenters faced a relentless enemy in rot, insects, and fire, and they fought back with a chemist's ingenuity. They developed a secret arsenal of wood preservatives, formulas that have kept timbers intact for 2,000 years. One of their most common defenses was a simple yet potent brew of vinegar and salt. They would boil this acidic mixture and brush it liberally onto wood, especially the parts that would be buried or exposed to moisture. The solution created an environment so hostile that fungi and wood-boring insects simply could not thrive. For shipbuilders and those working on exterior structures, another layer of protection was essential: heated resin. They would collect sap from trees like pine, heat it until it became a thick, sticky liquid, and then paint it onto planks and beams. This resin coating acted as a powerful waterproof sealant, locking out the dampness that leads to decay. It was the ancient equivalent of a heavy-duty marine varnish, protecting the mighty Roman trading vessels that crossed the Mediterranean. But the most surprising discovery came from archaeology: the use of lead. Analysis of preserved wood from Roman sites has revealed traces of lead-based compounds. It seems they sometimes used a paste made from lead and oil, or even vinegar, creating a toxic barrier that was lethally effective against pests. This was a double-edged sword, a brilliant preservative that unknowingly poisoned the artisans who applied it. These treatments were not applied haphazardly. They were the final, crucial step in a ritual of creation, a way of willing a structure to endure far beyond a single lifetime. This deep understanding of materials leads to an even greater question. How did they source the right wood in the first place? And what made the mighty oak so indispensable to their empire? While the marble and stone of Rome's grandest structures capture our gaze, their true origin story is written in wood. The Pantheon's majestic dome, the soaring arches of the Colosseum, these icons of stone were first born from a carpenter's vision. Before a single block of travertine was set, Roman carpenters would erect an enormous wooden skeleton, a temporary but perfectly engineered framework that defined the final shape. This was the secret cradle of Roman architecture. For a massive arch, they would build a sturdy curved form, known as a centering, that would hold the stones in place until the final keystone was locked into position. Only then, with the arch supporting itself, would they dare to dismantle the wooden ribs that gave it life. It was an act of faith in physics and their own craftsmanship. But their most breathtaking achievement was the dome. To build the Pantheon's vast ceiling, they constructed a colossal hemispherical scaffold, a wooden mountain rising inside the rotunda. Every detail of the complex coffered ceiling, every indentation, was first shaped in this temporary forest of timber. The masons then poured their concrete over this wooden mold, creating one of the most enduring marvels of the ancient world from a framework destined to be forgotten. Yet this hidden ingenuity extended far beyond the city. The aqueducts that marched across the empire relied on a carpenter's most daring work, the falsework. To span a deep valley, carpenters would first build a towering wooden trestle, a temporary bridge whose sole purpose was to support the stone channel as it was being built hundreds of feet in the air. This was carpentry at its most audacious, creating structures of immense strength and precision that were never meant to last, only to serve as a guide for something permanent. They were the ghost architects, their greatest work erased by the very monuments they made possible. But how did this knowledge, these secrets of joinery and form, survive the fall of an empire? The answer lies not in grand libraries, but in the quiet, persistent work of medieval monks. The fall of Rome did not mean its knowledge vanished into dust. It found sanctuary in the quiet, ink-stained hands of medieval monks, who meticulously copied and preserved the technical manuals of Roman engineers and architects. Within the scriptoriums of secluded monasteries, the secrets of joinery, geometry, and timber framing were painstakingly transcribed onto parchment, ensuring that the practical genius of the empire would not be lost to the Dark Ages. These manuscripts became the hidden seeds from which later European carpentry would eventually regerminate. Yet, nowhere was Roman carpentry more brilliantly applied or more critical to the empire's power than in the shipyards where its mighty fleets were born. Roman shipwrights approached their work not as mere assembly, but as a form of architectural logic applied to the unforgiving sea. Their most revolutionary concept was building a ship from the inside out. Instead of first laying a keel and attaching planks, they began by constructing the entire internal skeleton, the ribs and frames, with an astonishing degree of precision. Only when this robust wooden spine was complete would they carefully fasten the outer hull planks to it. This inside-out method created vessels of incredible strength and predictable form, allowing for the mass production of warships and merchant vessels on a scale that fed the empire's expansion. But a strong frame is nothing if the seams leak. To solve this eternal problem of the sea, Roman shipwrights developed a secret watertight joint system that made their vessels superior. They used closely spaced mortise and tenon joints to lock the hull planks together, but the true genius was in the sealing. They would drive the tenons tightly into their mortises, and then hammer a tapered wooden peg, called a trenail, through a hole drilled through both. This peg would swell upon contact with water, locking the joint permanently and creating a seal so tight it was nearly as solid as a single piece of wood. The entire hull became a monolithic, water-resistant shell, a floating fortress of joined timber. For centuries, this was considered the pinnacle of their craft, but a recent archaeological discovery has completely reshaped our understanding of Roman naval logistics. The excavation of a river port near Rome revealed something extraordinary: caches of pre-cut, standardized ship parts, keels, frames, and planks, all meticulously shaped and marked with Roman numerals, ready to be assembled. This was evidence of prefabrication on an industrial scale. It meant that Rome could ship these pre-made kits to any harbor in the Mediterranean, where local laborers with minimal specialized training could rapidly construct a fleet. This logistical masterstroke allowed Rome to project its naval power with a speed and efficiency that its enemies could not possibly match. The empire was not just built with wood and iron, it was built with a system of knowledge so advanced. Its components could be stored in a warehouse and its warships assembled on demand, anywhere the empire willed it. This same mastery of joinery and material science was not reserved for grand monuments alone. It found its way into the most intimate spaces of Roman life, their homes. Roman furniture was a world of hidden engineering, where everyday objects held secrets of structural genius. Take the simple folding stool, a common sight in forums and military camps. This was no flimsy deck chair. Its ingenious design relied on a complex system of pivoting joints and interlocking frames that allowed it to collapse into a compact bundle, yet lock into a rigid, stable seat when open. The precision required for these moving parts to function smoothly without metal hinges speaks volumes about the daily application of their carpentry skills. But for their more permanent household pieces, the true marvel was invisibility. A Roman dining table might appear to be supported by an elegantly carved leg, but often, hidden within that leg was a core of a different, stronger wood, a secret reinforcement that bore the load while the showier exterior provided the beauty. This practice of laminating woods, of combining different species for strength and aesthetics, reveals a nuanced understanding of material properties that feels remarkably modern. Perhaps the most surprising revelation, however, comes from their beds. We might imagine a simple wooden platform, but Roman beds were designed for comfort we are only now beginning to appreciate. They crafted frames from flexible woods like ash, creating a system of slats that would bend and rebound under weight, providing a spring-like support. They were engineering a good night's sleep centuries before the box spring, using the natural elasticity of wood to create a responsive, comfortable sleeping surface. This everyday luxury, this hidden comfort, was a direct result of their deep, almost intimate conversation with the material they mastered. They did not just build with wood, they listened to it, understanding how different grains and species could be coaxed into providing not just shelter, but ease and beauty. And this profound connection to their material would reach its ultimate expression in the one structure that defined the Roman world, the military machine. The same ingenuity that built flexible beds and prefabricated ships was harnessed to perform miracles of sheer strength. To lift the colossal stone blocks of their temples and amphitheaters, Roman carpenters became masters of mechanical advantage, constructing wooden cranes of such power they defied belief. The centerpiece of these machines was a massive treadmill, a giant wooden wheel turned not by muscle alone, but by the collective weight and effort of men walking endlessly inside it. This was a gear made of human beings, converting their steps into immense rotational force. But the true secret to their stability lay hidden in the counterweight system. These cranes were not simply anchored, they were balanced like a giant scale. Carpenters would calculate the precise weight of the stone to be lifted, and then suspend an enormous wooden box filled with heavy materials, often scrap stone or lead, from the crane's opposite arm. This counterweight acted as a perfect partner to the load, neutralizing the crushing force that would otherwise topple the entire structure. It was a dynamic equilibrium, a dance of opposing forces choreographed in wood and rope. This system allowed them to lift tons of stone with a control and safety that was unprecedented. The force was multiplied further by a sophisticated arrangement of pulleys. Roman engineers did not use a single rope over a single wheel. They employed complex block and tackle systems. By threading a rope through multiple, carefully aligned pulleys, they could dramatically increase the lifting power. A team of 5 men operating a 5-pulley system could, in effect, lift what would normally require the strength of 25 men. This was the magic of physics made tangible, a wooden machine that allowed human hands to move mountains. For centuries, we understood the principles, but we lacked the definitive blueprints. That changed with the discovery of fragmented architectural drawings, recently decoded by researchers. These are not simple sketches. They are detailed engineering plans scratched onto stone or etched onto wax tablets. They reveal crane configurations for specific monumental tasks, showing the exact placement of the treadwheel, the angle of the boom, and the complex routing of the ropes for projects once thought impossible. One such drawing appears to detail the lifting mechanism for positioning the massive lintels over the entrance to the Pantheon. These decoded plans are the final piece of the puzzle, proving that these were not improvised feats of strength, but carefully calculated acts of architectural ambition. They show us that the Roman carpenter, with his adze and his plane, was also a master of physics, his wooden machines standing as temporary titans that gave permanent form to an empire of stone. Beneath the sunlit monuments of stone lay another empire, one of perpetual darkness and unimaginable pressure. Here, far from the grand arches and aqueducts, Roman carpentry faced its most demanding task, not to create beauty, but to defy death itself. In the sprawling network of mines that fed the empire's insatiable appetite for gold, silver, and lead, carpenters descended into the earth to build skeletons of wood that held back the crushing weight of the world. Their work was not about permanence, but about providing a temporary shield for the miners who toiled in the gloom. The primary weapon in this subterranean war was a system of bracing so effective its principles are still used today. They constructed sturdy frames, often square or rectangular, known as cribbing. These were not solid walls of timber, but open cages built from interlocking logs, stacked one upon the other. The genius of this design was in its flexibility. The wooden cribs could absorb and redistribute the immense pressure from the tunnel roof, yielding just enough to prevent a catastrophic snap. It was a structure that understood it could not win a fight against the mountain, so it instead learned to dance with the pressure, guiding those forces safely into the surrounding earth. This system required an intimate knowledge of the enemy, the ground itself. Roman engineers and carpenters became adept at reading soil and rock conditions, and they selected their timber accordingly. In stable, dry rock, they might use a resilient wood-like elm for its resistance to splintering. But when digging through wet, unstable clay that threatened to flow like a river, they turned to the water-resistant powers of oak or larch. These woods contain natural oils and tannins that act as a preservative, allowing them to withstand the damp, rotting environment that would quickly destroy lesser timber. They were not just picking trees, they were matching the personality of the wood to the personality of the earth. The ultimate test of their skill was in driving long tunnels through soft ground. Here, they employed a technique called forepoling, a desperate and brilliant race against time. As miners dug forward, carpenters would immediately drive sharpened wooden planks, almost like giant spears, up into the tunnel ceiling just ahead of the working face. These planks would create a protective canopy under which the miners could work, preventing loose soil from collapsing on them before the permanent cribbing could be installed. It was a high-stakes ballet of excavation and shoring, a testament to their commitment to pushing the boundaries of the possible while guarding human life. And we know this system worked, not just from ancient texts, but from the chilling evidence left behind. In mines across Europe, from Spain to Romania, archaeologists have ventured into ancient galleries and found Roman timber supports still standing after 2,000 years. In some cases, the wood is so well preserved you can still see the tool marks from the adze that shaped it, a ghostly signature from the carpenter who left it there to hold up the darkness. These silent, enduring frames are perhaps the most powerful legacy of Roman carpentry, a reminder that their greatest secret was not just how to build for the ages, but how to build for the survival of the person in the dark, trusting their life to a framework of wood. While carpenters braced the darkness of the mines, their colleagues were solving a puzzle of a different kind, mastering the delicate balance of fire and wood to bring warmth into the heart of the Roman home. This was the mystery of the hypocaust, a hidden heating system of astonishing sophistication. In the villas of the wealthy and the grand public baths, the floors were not cold stone, but living structures, gently warmed from below. The carpenter's first and most critical task was to build the very foundation of this heat, a raised wooden floor. They did not simply lay planks over the fire that would have been a death sentence for the wood. Instead, they constructed a forest of small, squat pillars, called pili, from specially selected clay or brick. Onto this stable, fireproof grid, they then fastened a complex wooden framework. This framework had to be perfectly level and incredibly sturdy, for it would support the heavy tile and concrete of the floor above, a floor that people would walk upon, unaware of the fiery breath below. The wood was in a constant battle against two relentless enemies: the intense dry heat from the furnace and the pervasive steam and moisture from the baths themselves. How did they prevent this wooden skeleton from warping, cracking, or rotting under such an assault? The answer lies in a profound understanding of wood itself. Roman carpenters knew that different woods reacted to heat and moisture in unique ways. They favored woods like oak and elm for these frameworks, species known for their density and resistance to movement. They would also season the wood for years, allowing it to naturally dry and stabilize long before it was ever placed near a furnace, minimizing the internal stresses that cause warping. But their true genius was in the design of the hidden space itself. They engineered a small but crucial air gap between the wooden framework and the heated pillars below. This gap acted as a buffer, a cushion of air that prevented direct conductive heat from scorching the wood. It allowed the warmth to radiate upwards gently, heating the mass of the floor above without directly attacking the wooden support structure. This was climate control engineered in wood, a system that managed thermal energy with the precision of a modern engineer. Modern studies of surviving hypocaust systems reveal something even more remarkable: evidence of primitive vapor barriers. It appears they sometimes coated the wooden framework with a layer of clay or a mix of lime and crushed pottery, creating a shield that blocked destructive moisture from the bath steam below, while still allowing the gentle, radiant heat to pass through. This delicate balancing act, this orchestration of materials against elemental forces, is a lost art that modern engineers are only now beginning to fully appreciate and decode. The Roman carpenter did not just build a floor, he built a machine for living, a hidden ecosystem of comfort that has yet to be fully replicated. The warmth of the hypocaust was a delicate dance, but the true test of Roman carpentry came with the relentless power of flowing water. To make wood survive for centuries in the constantly wet environments of baths and aqueducts, they developed a multi-layered defense system that was nothing short of alchemical. Their first line of defense was a secret weapon from the beehive beeswax. After meticulously planing a plank to a glassy smoothness, carpenters would rub it vigorously with blocks of raw wax. The friction of this polishing would generate heat, melting the wax and driving it deep into the wood's pores. This was not a simple surface coating. It created a hydrophobic barrier from within, causing water to bead up and roll away instead of being absorbed. For the wooden sluice gates that controlled the flow of aqueducts, this wax treatment was essential, preventing the swelling and warping that would have jammed the mechanism. But wax alone could not withstand the torrent. For the massive water wheels and the constantly submerged support pilings of their bridges, they turned to a more robust solution: the layered resin seal. They would begin by charring the surface of the wood lightly with fire. a process that created a layer of carbon that was naturally resistant to rot and insects. Then, while the wood was still warm, they would apply multiple coats of heated pine resin, each layer painstakingly brushed on and allowed to cool and harden before the next was added. This created a thick, flexible, and incredibly durable shell, a synthetic bark that was far more impervious to water than the wood's own surface. The final coat was often a mixture of resin and olive oil, giving it a slick, self-healing quality that could withstand minor abrasions from debris in the water. This was the ancient equivalent of industrial-grade epoxy, a testament to their understanding of material chemistry. Yet the most astonishing discovery emerged from the silt of a preserved Roman harbor, the use of lead sheathing. Archaeologists found the remains of wooden pipes and aqueduct troughs that were not just coated, but entirely clad in thin, hammered sheets of lead. This was not a mere preservative, it was a complete environmental isolation. The lead acted as an impenetrable barrier, protecting the wood from water, from boring shipworms, and from the corrosive minerals in the water itself. The carpenters would fashion the wooden core with special grooves and channels, and then the metalworkers would carefully mold the soft lead around it, creating a perfect, seamless union of wood and metal. This technique was reserved for the most critical components, the ones where failure was not an option. It reveals a mindset that went far beyond simple maintenance. They were engineering for eternity, willing to use the empire's most valuable resources to ensure their wooden structures would outlast the very stone that stood beside them. That same understanding of wood, honed in mines and bathhouses, was forged into a weapon of war. The Roman legionary marched with more than just a sword and shield. His true strategic advantage was the carpenter who marched beside him. These men were the unsung heroes of the military machine, a dedicated corps of engineers who could reshape the landscape itself in a matter of hours. Their most vital skill was the construction of the marching camp, a fortified city built from nothing at the end of every day's march. Each soldier carried 2 sharpened wooden stakes, and upon selecting a site, the carpenters would direct the entire legion in a choreographed routine of digging and building. They erected a palisade, a defensive wall of those same stakes, set into a pre-dug trench and earth rampart. The gates were not weak points, but complex wooden structures with reinforced posts and swinging doors, all assembled with standardized joints that every soldier was trained to fit together. This was not a haphazard barrier. It was a prefabricated fortress unpacked from the backs of 5,000 men, a testament to logistics and speed. But their true mastery was demonstrated when the army faced an impassable river. The story of Julius Caesar's crossing of the Rhine in just 10 days is a legend of military carpentry. Rather than relying on slow, vulnerable boats, his engineers built a timber bridge over a river 300 meters wide. They did not fell trees on the spot. They used a prefabricated system. The bridge's components, massive pilings, and pre-cut crossbeams were prepared in advance and transported by wagon. The carpenters used giant wooden pile drivers, swung by teams of soldiers, to hammer the sharpened pilings deep into the riverbed. Then, using a system of lap joints and mortise and tenon, they locked the pre-fitted framework together atop these supports. The entire structure was a modular kit, designed for rapid assembly under combat conditions. This bridge was not just a crossing, it was a statement of power, a symbol that no natural barrier could halt the Roman army. For siege warfare, their carpentry became an art of controlled destruction. They built massive towers, taller than the enemy's walls, on wheels hewn from entire tree trunks. These were not crude lumber piles. They were multi-story wooden buildings on the move, protected from fire by hides soaked in vinegar and water. Inside, complex pulley systems, operated by teams of men, would raise and lower internal ramps. The precision required for these moving parts, all crafted from wood and operating under the stress of combat, is almost unimaginable. The battering ram itself, the testudo, was a masterpiece of protected joinery. It was not a single log carried by men, but a massive timber suspended within a long, roofed shed on wheels. The entire structure was covered in wet clay and animal hides to resist fire, and the ram was swung on ropes from a meticulously engineered frame. This allowed a rhythmic, powerful momentum to build, focusing immense force onto a single point on the enemy's gate. The designs for these machines were so effective they were guarded military secrets, passed down through the Corps of Engineers. This was the ultimate expression of Roman carpentry, not just building for permanence, but for instantaneous, overwhelming force. They turned forests into fortresses and bridges, proving that the most powerful empire in the world was, at its heart, built by the hands of carpenters. The legion's ability to build bridges in days was matched only by their skill in bending wood itself, a quiet art that gave Roman architecture its signature curves. We often assume that shaping wood into elegant arcs requires the intense heat of steam, but Roman carpenters mastered a different path, one of patience and chemical persuasion. Their secret began with the careful selection of green wood, freshly felled timber still rich with its natural moisture. They understood that wood was most pliable when its cellular structure was full of water, like a living sponge. But they did not simply force it into shape. Instead, they employed a controlled drying process, often in specialized sheds where temperature and humidity could be managed. A carpenter would rough cut a piece to its general shape, then clamp it into a curved form, a rigid wooden jig carved into the exact arc he desired. The wood was not left to dry quickly, that would cause it to split and crack. It was held captive in this curved prison for months, sometimes even years, slowly surrendering its moisture while its very fibers memorized the new, permanent bend. It was a battle against time and tension, a gentle coercion that resulted in a curve of incredible strength and stability. For more immediate needs, they turned to chemistry. They discovered that soaking wood in certain solutions could break down the stiff bonds between its fibers. One common treatment was a simple bath of vinegar and water, the mild acid softening the lignin, the natural glue within the wood. For tougher jobs, they might use a more potent mixture of stale urine, which contains ammonia, or even a solution of quicklime. These chemical baths made the wood temporarily supple, allowing it to be bent around forms with far less force, and then clamped until it dried and hardened into its new shape. The final piece of the puzzle was the clamping system itself, a marvel of mechanical ingenuity. They used windlasses and rope tourniquets to apply immense, even pressure, but their true genius was the use of wedges. A carpenter would build a sturdy frame around the wood and its form, then drive a series of wooden wedges into the gap between the frame and the workpiece. With each precise tap of his mallet, he would incrementally increase the pressure, guiding the wood into its curve with a level of control that a single, powerful clamp could never provide. You can see the legacy of this technique in the curved ribs of Roman ships, in the gracefully arched backs of their dining couches, and in the sweeping wooden frames that supported vaulted ceilings. This was not brute force. It was a conversation with the material, a deep understanding of how to persuade a rigid beam to embrace a beautiful, enduring curve. The gentle curve of a ship's rib was not born from guesswork. but from a hidden language of numbers. Roman carpenters were, in their own way, mathematicians, wielding geometry as their most fundamental tool. They saw the world not as chaotic shapes, but as a series of perfect, calculable relationships, and they embedded this mathematical soul into everything they built. The most famous of these relationships is the golden ratio, a proportion found throughout nature, from the spiral of a nautilus shell to the arrangement of seeds in a sunflower. The Romans called it the divine proportion, and they applied it with deliberate artistry. When a master carpenter designed a prestigious piece of furniture, like a senator's lectern or a wealthy household storage chest, he would often use this ratio to determine its dimensions. The height of the chest might relate to its width in this specific, harmonious proportion, around 1.618 to 1. This wasn't just about aesthetics, though the result was undeniably pleasing to the eye. It was about creating a subconscious sense of balance and stability, a structure that felt inherently right and solid because it echoed the very patterns of the natural world. This mathematical harmony extended to the floors beneath their feet. In the grandest villas, intricate geometric patterns known as opus sectile were laid out in marble and stone, but the complex design work, the precise division of space into triangles, squares, and hexagons, was first mapped out on a full-scale wooden template. The carpenter was the one who translated the architect's vision into a tangible guide, using ropes, stakes, and a simple but powerful tool called a groma to establish perfect right angles and straight lines. They would calculate the intersections, ensuring that every star and every diamond fit together without a single gap. A puzzle solved with string and geometry long before the first piece of costly stone was ever cut. But this mathematical precision reached its peak in structural calculations, where a simple miscalculation could mean collapse. How did they determine the exact thickness of a roof beam needed to span a vast bathhouse? They relied on established rules of thumb, refined over generations, that were essentially practical applications of geometry and physics. A carpenter knew that to double the span a beam could safely cover, he didn't just double its thickness, he had to increase its depth exponentially. This intuitive understanding of load distribution was a form of lived mathematics, a set of formulas encoded not in textbooks, but in the collective memory of the guilds. They used simple, repeatable geometric constructions to lay out complex joints, ensuring that the angled cuts on a scarf joint or the dovetails in a strongbox would lock together with unwavering accuracy. Every cut was a calculated decision, every measurement part of a greater equation whose solution was a structure that could stand for centuries. A carpenter's first and most critical choice was not his tool, but his timber. While we remember the mighty oak for ships and the fragrant cedar for chests, Roman woodworkers possessed a far more nuanced understanding, treating each species like a specialized tool in its own right. For tasks demanding absolute precision, they turned to boxwood. This was not a timber for building walls, but for carving the soul into a piece. Boxwood is incredibly dense and fine-grained, allowing a craftsman to cut the most delicate details without the wood splintering or chipping. They used it for the intricate inlay on a senator's chair, for the tiny, moving gears of an astronomical model, or for the complex facial features of a wooden deity. Its hardness meant it could hold a razor-sharp edge, making it the perfect material for the wooden screws and gears within their presses and measuring devices. This was a wood chosen for its ability to hold a thought, to make an idea permanently tangible in a way that coarser wood simply could not. For a completely different challenge, they relied on the unassuming elm. Everyone knew oak was strong, but elm possessed a hidden superpower, an almost supernatural resistance to splitting. When subjected to repeated impacts and shocks, oak can fracture along its grain. Elm, however, has an interlocking, twisted grain structure that defies such clean breaks. This made it the undisputed champion for applications where toughness was paramount. They used it for the hubs of wagon wheels, the part that receives the brutal, constant pounding from the axle. They shaped it into the chopping blocks for butchers and the massive mallets used by stonemasons. But its most ingenious use was in waterworks. While oak was used for ship hulls, elm was often the secret star below the waterline, for the pumps that lifted water from mines and for the pipes within their complex plumbing systems. Elm was a superior choice. Its interlocked grain made it less prone to splitting under constant water pressure, and it resisted the rotting effects of perpetual dampness far better than many of its contemporaries. This was a choice made not from tradition, but from a deep empirical knowledge of material performance under stress. They even understood the hidden life within a tree, how its history shaped its strength. A carpenter seeking wood for a powerful bow would not just grab any piece of you. He would seek out a stave cut from the side of the tree that grew under constant tension, where the wood fibers were naturally compressed and primed to store immense energy. He was reading the tree's life story written in its rings and using that narrative to his advantage. This was not mere carpentry, it was a form of botanical alchemy, a forgotten science of matching the unique personality of a wood to the specific demands of a task, creating a synergy between material and purpose that modern woodworking is only beginning to rediscover. This mastery of wood selection was only the beginning, for the true soul of Roman carpentry was often revealed in its final, most expressive form, intricate carving. We tend to envision Roman woodwork as purely structural, all beams and joints, but this overlooks an entire world of artistic expression, a lost art of transforming timber into breathtaking sculpture and decoration. They achieved this with a specialized set of carving chisels, tools so refined that many were misidentified by early archaeologists. Beyond the standard flat chisel, they employed gouges with subtly curved blades for scooping out channels, V-parting tools for slicing crisp, clean lines, and veiners, which are incredibly narrow, deep gouges for detailing folds in drapery or strands of hair. The most telling tool, however, was the spoon-back gouge. This chisel had a curved shaft and a U-shaped blade, allowing the carver to work deep within a recess without the handle hitting the surrounding wood. It was the essential instrument for undercutting, a technique that gave their relief carvings a stunning, three-dimensional life. This illusion of depth was their greatest trick. A Roman craftsman did not simply carve a figure onto a flat panel. He used a method of layered carving to create a powerful sense of space. He would first outline the entire scene, then carve the background down, leaving the central figures raised. But the magic happened next. Using those specialized gouges, he would undercut the edges of the raised figures, carving backwards and underneath them. This created a physical shadow line, separating the figure completely from the background. To the eye, the figure appeared to float, completely detached from the wooden plane behind it. They enhanced this effect with masterful texturing, using a tiny, toothed chisel called a claw to create the rough texture of a lion's mane or the weave of a tunic, while using polished smoothing stones to make the skin of a goddess appear soft and luminous. The result was a panel that seemed to breathe, a shallow piece of wood that held a world of depth and movement. For centuries, the consistency of these decorative patterns on everything from furniture to architectural panels seemed too perfect to be done freehand. The discovery of a cache of thin, reusable templates in the workshop of a Herculaneum carpenter finally revealed their secret. These were not simple stencils, they were sophisticated guides, often made of bronze or hardened wood, carved with complex geometric borders, acanthus leaves, and mythological figures like griffins or cupids. A carpenter would clamp the template to his workpiece and trace the outline with a fine stylus. But here is the real genius: many templates were multi-layered. One template would establish the core shape of a leaf, while another, placed over it, would guide the carving of the individual veins and serrations. This system ensured that every acanthus leaf curling across 100 different ceiling panels in a basilica was identical, a signature of mass-produced beauty that maintained the highest level of artistic integrity. It was a system that combined the efficiency of an assembly line with the soul of an artist, proving that their drive for perfection was etched not just in wood, but in metal and method. The most breathtaking structures in Rome were often those never meant to last. For the grandest games and most triumphant celebrations, carpenters would perform a kind of architectural magic, erecting colossal temporary theaters and amphitheaters that could hold tens of thousands of spectators, only to vanish without a trace once the festival was over. These were not flimsy bleachers, but monumental wooden buildings engineered for both safety and speed. The secret to their rapid assembly lay in an ingenious system of prefabrication and interlocking joints. Every beam, every raker, every seat support was pre-cut to exact dimensions and marked with a simple coding system. The joints themselves were marvels of temporary design, often using a complex variation of the scarf joint, where two timbers were notched to overlap and then locked with a removable wooden key or a tapered peg. This created a connection as strong as a permanent building, yet one that could be disassembled with a few strategic hammer blows, allowing the entire structure to be broken down into a kit of parts and stored for the next spectacle. The sheer scale of these projects was staggering. Historical accounts describe a temporary theater built by Marcus Scaurus that held 81 people, a structure adorned with thousands of marble columns and bronze statues, all supported by a hidden wooden skeleton of unimaginable complexity. For centuries, we assumed these descriptions were exaggerations, the boasts of rich politicians, but a recent discovery has changed everything. In the archives of a European library, researchers uncovered a fragment of a Roman construction manual, a papyrus scroll detailing the assembly of a temporary amphitheater. This is not a philosophical treatise, it is a practical guide, complete with diagrams. The drawings show the exact sequence for raising the tiered seating, known as the cavea, and specify the order in which the key structural ribs had to be locked into place to ensure stability under the weight of a roaring crowd. It describes a system of numbered posts and coded braces, a literal instruction manual for building a city within a city, and then erasing it from existence. This manual confirms that these ephemeral masterpieces were not acts of chaotic improvisation, but the result of meticulous planning and a deep understanding of structural physics applied to the most fleeting of canvases. They prove that Roman carpentry's ultimate secret was not just how to build for eternity, but how to conjure grandeur from thin air, creating unforgettable experiences out of timber and sweat. The same principles that raised the Colosseum stones were also harnessed to power the empire's bustling workshops. Hidden away in industrial districts, Roman carpenters built sophisticated wooden machines that automated tasks on a scale the world had never seen. One of their most ingenious creations was the fulling mill, a machine that revolutionized the cloth-making industry. Before this invention, Cleaning and thickening woolen cloth was a brutally physical process, with workers trampling fabric in vats of stale urine and clay. The Roman solution was a water-powered mechanical foot. They channeled water to turn a large wooden wheel, which, through a series of precisely carved cogs and gears, converted the smooth rotation into the pounding motion of a series of heavy wooden hammers. These hammers would rise and fall rhythmically onto the cloth in the vats, filling it with a consistent, powerful force that human legs could never match. This was not just a labor-saving device. It was the world's first industrialized laundry, a wooden robot tirelessly performing the work of dozens of men. The true mechanical genius, however, was reserved for feeding the empire. To grind the mountains of grain needed for Rome's daily bread, they perfected the geared grain mill. At its heart was a vertical water wheel, a colossal structure of oak and elm. But the power from that wheel had to be turned 90 degrees to drive the heavy millstones. This is where their carpentry reached its peak. They achieved this with a crown gear, a wooden gear with teeth set at a right angle to its face, meshing perfectly with a horizontal gear called a lantern pinion. Carving these gears from durable woods like boxwood or hornbeam required an artist's touch and an engineer's mind. Each tooth had to be identically shaped and spaced, or the mechanism would jam under the immense strain. The entire assembly, from the water wheel's axle to the spinning millstone, was a symphony in timber, a machine that could run for days, transforming flowing water into the flour that sustained a city of 1 million people. Beyond these large industries, this mechanical ingenuity filtered down to the craftsman's bench. Roman carpenters built specialized wooden machines for manufacturing, tools that represented the absolute peak of pre-industrial technology. They had elaborate lathes, powered by a bow or a foot treadle, which could spin a piece of wood against a fixed chisel, allowing them to produce perfectly symmetrical table legs, bowls, and even intricate balusters with astonishing speed and consistency. For metal workers, they constructed massive wooden drop hammers, lifted by cams on a rotating shaft, and then released to fall with tremendous force, shaping hot metal into tools and weapons with a uniformity that was essential for the legions. These were not isolated inventions. They were part of an integrated system of production. The wooden gears from the grain mill shared design principles with the gears in a carpenter's own drills and presses. This was a technological ecosystem built almost entirely from wood, a testament to a civilization that had learned to make the forest itself think, calculate, and labor on an industrial scale. How did this vast, interconnected knowledge, from the shipyard to the workshop, finally come to an end? The answer lies not in a single catastrophe, but in a slow fading of light, a story of how an empire's memory was lost to time. A flawless joint or a perfectly carved panel was only the beginning of the Roman carpenter's work. The final, transformative act was the finish, a secret alchemy of color and protection that turned simple wood into an object of enduring beauty. They began with color, but not from simple paints. They sought out vibrant, natural dyes from the most unexpected places. The rich, imperial purple we associate with togas could be mimicked for furniture inlays using a dye extracted from a specific type of lichen. For a deep ruby red, they turned not to berries, but to a tiny insect, the kermes, which they would carefully collect from the branches of oak trees and crush into a potent powder. A brilliant yellow came from the saffron crocus, while a soft green was derived from soaking copper filings in vinegar, creating a toxic but stunning verdigris paste. These were not mere coatings. They were stains that penetrated deep into the wood's grain, enhancing its natural character rather than hiding it. The true magic, however, happened next with the wax. This was not a single, simple application. The Roman finish was a ritual of layers. They would first warm the wood slightly, often by leaving it in the sun. Then, using a cloth pad, they would rub in a first thin coat of beeswax, sometimes mixed with a little olive oil to keep it pliable. They allowed this to fully harden for a day. The following day, they would buff it vigorously with a bundle of rough horsetail grass, which acted like a natural sandpaper, smoothing the wax and driving it deeper. Then came a second coat and another round of polishing, this time with a softer cloth. This process of layering and burnishing could be repeated 5 or 6 times, each cycle filling the microscopic pores in the wood a little more, building up a deep satin glow that came from within the surface, not from a shiny coating on top. The final step was a high-gloss polish achieved with a surprising tool, a smooth, water-worn river stone. The carpenter would spend hours rubbing the stone in small, fast circles over the surface, the friction generating just enough heat to slightly melt the outermost layer of wax, fusing it into a seamless, glass-like shell. This finish was not just beautiful, it was incredibly functional. The wax itself repelled water, while the hard, polished surface resisted scratches and everyday wear. You can still see the ghost of this luster on rare, preserved fragments of Roman furniture, a sheen that has survived 2 millennia. This dedication to the final surface reveals a profound truth. For the Roman carpenter, beauty was not an afterthought. It was the final, essential layer of strength, a protective skin that declared an object was not merely built, but perfected. That luminous finish on a perfect piece of furniture was more than just a craftsman's pride. It was the signature of a system. The secrets of Roman carpentry, from joinery to geometry, did not spread by accident. They were protected and propagated by a hidden network, the carpentry guilds. These were not simply trade unions. They were the living libraries of the empire's technical knowledge, and their primary mission was to safeguard their craft's most valuable asset, its methods. A young boy entering a guild as an apprentice was embarking on a journey of silent learning. His first years were spent not with a chisel, but with a broom watching. He would observe the master's posture, the angle of his grip on the adze, the specific sound a plane made when taking the perfect curl. Knowledge was transmitted through demonstration and mimicry, a slow, deliberate process where the hands learned what words could never fully capture. The apprentice learned the feel of seasoned oak versus green elm, the subtle difference in resistance that told him how to adjust his cut. This was an education built on muscle memory and inherited instinct, ensuring that the guild's standards of quality were literally embodied in its members. The ultimate goal for the most gifted was to produce a masterpiece, a piece of work that demonstrated complete mastery of the craft, which then granted him the status of a journeyman, allowing him to travel and work under other masters, cross-pollinating techniques across the vast Roman world. But alongside this oral tradition existed something even more precious and far more fragile, the technical manuals. We know from references in texts like Vitruvius's that detailed, illustrated manuals on carpentry and machinery existed. These were not for public sale. They were the guild's protected intellectual property, likely copied by hand and guarded fiercely. They contained complex diagrams for constructing cranes, laying out geometric patterns for inlay, and precise recipes for wood preservatives and finishes. The tragic truth is that almost none of these woodworking manuals survived the fall of Rome. Written on perishable papyrus or parchment, they crumbled away, leaving only echoes of their existence in the architectural fragments we dig up today. This is why the discovery of those assembly instructions for a temporary amphitheater was so monumental. It was a rare, tangible piece of this lost literary tradition. Yet, even without these texts, we have overwhelming evidence of a knowledge network in action. A dovetail joint from a chest in Roman Britain is cut with the exact same proportions and angles as one from a workshop in Syria. The specific design of a water-lifting device found in a Spanish mine is functionally identical to one depicted on a relief in Germany. This consistency across thousands of miles points to a rigorous system of quality control and shared technique maintained by the guilds. When a master carpenter from Gaul was commissioned for a project in North Africa, he brought his guild's methods with him, and in return, he learned about local woods and adaptations, carrying that knowledge back home. The guild was the empire's silent, decentralized university for the building arts, ensuring that a standard of excellence could be reconstructed from Britain to Egypt, creating a unified architectural language written not in stone, but in wood. Those guild secrets and geometric principles were tested to their absolute limit when carpenters confronted a rushing river. A Roman wooden bridge was a paradox, a permanent structure built with techniques for temporary speed. Its greatest challenge lay hidden beneath the water's surface, in the shifting, unstable riverbed. To solve this, they developed an ingenious foundation system known as the timber crib. Instead of trying to drive a single massive piling into soft silt, they would construct vast, open boxes from interlocking logs, assembling them on the riverbank and then sinking them into precise positions on the river floor. These cribs were not solid, but open frameworks, and their genius was in what happened next. Workers would fill the hollow cribs with thousands of stones until the immense weight anchored the entire structure firmly against the current. This created a stable, distributed platform that would not sink or tilt. A man-made island of wood and stone from which the bridge's main supports could rise. But for the longest spans, where the central piers were impossible, they employed a hidden reinforcement technique that defied the apparent limits of wood. They built trusses. A truss is a framework of triangles, and the Romans understood that a triangle is the only rigid geometric shape. By arranging beams into a series of these interlocked triangles, they created a bridge deck that was incredibly strong and lightweight. The weight of a crossing wagon was no longer borne by a single, thick beam, but distributed as tension and compression forces along the many members of the truss. This allowed them to span distances that would have required impossibly massive solid timbers, turning a potential weakness into a triumph of engineering physics. The evidence for their systematic approach has long been inferred from ruins, but a recent discovery on the banks of the Danube has provided stunning confirmation. Archaeologists unearthed a Roman military supply depot containing not finished bridges, but bridge kits. There were stacks of pre-cut timbers, each one marked with a specific code and a Roman numeral. The joints on these beams were standardized mortise and tenon, designed to fit together in only one way, like a giant, waterproof puzzle. This meant that a team of soldiers with minimal carpentry training could rapidly assemble or repair a critical river crossing by simply following the assembly codes. They could even replace a single damaged truss segment without dismantling the entire structure. This modular thinking transformed a bridge from a monumental construction project into a maintainable, repairable asset. It was the ultimate expression of the Roman carpenter's genius, creating structures of enduring strength from a system designed for swift and certain renewal. The same ingenuity that built bridges and siege engines was quietly reshaping the Roman countryside, turning fertile land into an empire's breadbasket. At the heart of this agricultural revolution was a tool of deceptive simplicity, the Roman plow. This was no mere pointed stick dragged through the earth. The most advanced models, known as wheeled plows, were complex wooden machines. They featured a heavy, iron-tipped share to slice the soil. But the true innovation was the moldboard, a curved wooden plate mounted behind the share. As the plow was pulled forward, this moldboard would catch the sliced sod and smoothly turn it over. This simple act of inversion was transformative. By burying weeds and the stubble of the previous crop, it fertilized the soil naturally and eliminated competition for the new seeds, all in a single pass. The addition of a front wheel allowed the farmer to maintain a consistent depth, turning back breaking labor into a controlled, efficient process. This wooden and iron partnership unlocked the dense, rich soils of Northern Europe, soils that had previously resisted simpler plows, allowing the empire to feed its legions and its sprawling cities. Once the field was sown, the next challenge was protecting the harvest from its greatest enemy, rot. Roman granaries were masterclasses in environmental carpentry. They were not just wooden sheds, but carefully engineered climate control systems. The floors were raised on a grid of low pilings, creating a crucial air gap that prevented ground moisture from seeping upwards. But the real secret was in the walls, which were built as double layers with a hollow cavity between them. This dead air space acted as a powerful insulator, buffering the precious grain inside from the temperature swings of the hot Italian summer. Ventilation was precisely managed through a series of louvered shutters, their angled slats carved to allow air to circulate while keeping driving rain completely out. Inside, complex wooden ducts channeled this airflow evenly throughout the entire storage volume, preventing the damp, stagnant pockets where mold and pests could take hold. This was food preservation engineered in wood, a system that could keep grain edible for years. Yet the most financially valuable crop required an even greater mechanical touch. The olive press was where Roman carpentry reached its peak of elegant efficiency. The traditional lever press was a monumental structure, using a giant wooden beam, counterweights, and immense manpower to slowly squeeze oil from crushed olives. But Roman engineers refined this into a more compact and powerful machine, the screw press. The centerpiece was a massive wooden screw, a feat of carving so precise its threads had to be perfectly symmetrical to bear the tremendous pressure without splitting. This screw was turned by a long wooden spoke, a capstan that allowed multiple workers to walk in a circle, applying their combined force with steady mechanical advantage. The crushed olives were contained in stacked, woven baskets called fiscali, and as the giant screw turned, it pressed down a wooden plate, squeezing every last drop of precious oil from the fruit. The resulting liquid was channeled through carefully carved grooves in a stone base into waiting amphorae. This was not brute force, it was a calibrated extraction, a wooden machine that turned a seasonal harvest into the liquid gold that lit lamps, dressed food, and wealthified the empire. In the quiet of the farmstead, far from the roar of the Colosseum, these wooden innovations were building an empire just as enduring, one harvest at a time. Every Roman beam and plank held a hidden message, a code scratched into its surface that directed the entire assembly process. These were not random scratches, but a sophisticated system of carpenter's marks, a silent language of construction that ensured every piece found its proper place. On a massive temple rafter, you might find a simple Roman numeral like 7 or 12, carved deep into the wood. This was not a count, but a coordinate. It told the raising crew exactly which of the many identical-looking beams this one was, and precisely where it belonged in the grand sequence of the roof's framework. Without these numbers, the complex puzzle of a building's skeleton could never be locked together, but the system went far beyond simple counting. Archaeologists have found timbers marked with a series of deliberate notches and dots. At first glance, they appear meaningless, but analysis reveals they are a form of quality control. A certain pattern of 3 dots might signify that this piece of oak passed inspection for being straight-grained and free of knots, making it suitable for a critical load-bearing joint. Another symbol, perhaps a small carved circle, could flag the wood as having a slight warp, directing it to a less structurally demanding role. This was a method of grading material long before modern lumberyards, a way to sort strength from weakness with a single, swift mark. The most personal of these symbols were the workshop signatures. Just as an artist might sign a painting, a master carpenter would often stamp his timber with a unique emblem. This could be a simplified tool, like a tiny adze or a drill bit, or a more abstract geometric design. Discovering 2 beams with the same workshop mark miles apart tells a powerful story of economic networks. It means a single, trusted workshop in a city like Ostia was producing prefabricated components that were then shipped across the empire to build a bridge in Gaul or a barn in North Africa. This signature was a badge of honor and a guarantee of quality, a promise that the piece was crafted by hands trained in a specific tradition. For centuries, these marks were dismissed as simple tallies. The breakthrough in decoding them came from a recent study of waterlogged timbers from a Roman port. Researchers realized that the marks were not isolated, but formed a complete instruction set when read in sequence on multiple pieces. A numeral would tell you the beam's position, a quality mark would confirm its integrity, and an assembly symbol, like a small arrow or a V, would indicate which face should be oriented upward or outward. Some of the most complex symbols appear to be miniature diagrams of the joint itself, showing the carpenter where to make his cuts. This was a language without vowels, a technical shorthand that allowed for the rapid and error-free construction of everything from humble shops to imperial barges. It reveals a world where wood was not just a raw material, but an information system, each piece carrying the intelligence required for its own placement in a grander design. That same silent language of carpenters' marks made something else possible, an empire-wide system of wood recycling that was centuries ahead of its time. Roman carpenters viewed wood not as a disposable material, but as a valuable resource to be perpetually reused. When a trading vessel grew too old for the sea, its end was not a fiery pyre but a transformation. Shipwrights would carefully dismantle the hull, saving every usable plank and beam. The massive oak keel of a retired cargo ship might find new life as the central roof beam in a wealthy merchant's villa, its curved shape a ghost of the waves it once rode. The thick, resilient hull planks, already shaped and sealed for maritime duty, were prized for their stability and often became flooring or were repurposed into the sturdy frames for city gates. This was not a haphazard salvage operation. It was a calculated redeployment of seasoned, high-quality timber. The evidence is etched into the wood itself. Archaeologists have found timbers in Roman buildings that still bear the distinct, tightly spaced mortise and tenon joints characteristic of ship construction, joints that were simply incorporated into the new building's design. This practice of repurposing was driven by a deep understanding of wood's life cycle. A carpenter knew that wood which had already seasoned for decades in a ship's hull was far less likely to warp or crack in its second life as a building component. It was a pragmatic form of sustainability, ensuring that the immense investment of labor and material captured in a ship was never truly wasted. But their conservation efforts went even further into the delicate art of repair. They did not simply discard a cracked beam or a worm-eaten plank. They practiced intricate surgeries on damaged wood. A long split in a critical roof timber would be carefully opened, filled with a special glue made from animal collagen, and then clamped tightly until the bond was stronger than the surrounding wood. For more severe damage, they would craft a custom patch, a new piece of wood shaped to fit the flaw perfectly and fastened in place with hidden dovetails or locked with wooden butterfly keys. These repairs were not hidden scars. They were testaments to a philosophy of preservation, a commitment to extending the life of every piece of timber for as long as humanly possible. This entire system of reuse and repair depended on a stable, long-term supply, which leads to the final, crucial piece of the puzzle, the Roman-managed forest. Contrary to the image of an empire clear-cutting its landscape, evidence is mounting that they practiced sophisticated forestry. Inscriptions and land surveys describe tracts of woodland designated as imperial forest, reserved for shipbuilding and construction. They understood the concept of rotational harvesting, selectively felling mature trees while leaving younger ones to grow, ensuring a continuous supply for future generations. They even had preferences for how trees were grown, knowing that oak grown in dense stands would produce taller, straighter trunks with fewer knots, the ideal material for the masts of their mighty warships. This was not just resource extraction. It was a form of long-term partnership with the land. The Roman carpenter, with his recycled ship timber and his repaired beams, was part of a vast, interconnected system that saw the forest not as an endless resource to be plundered, but as a living, breathing foundation for an empire that was built, quite literally, to last. 25 secrets later, we are left with a profound realization. The grandeur of Rome was not built on marble and conquest alone. It was first framed in wood, joined with a precision that defied time, and sealed with an understanding of nature we are only now relearning. This carpentry was the silent, indispensable partner to every legion's march and every aqueduct's graceful arc. It was the hidden logic behind the empire's reach and resilience. Today, as we grapple with the environmental cost of our own building practices, these ancient techniques offer more than just historical fascination. They present a compelling challenge. What if we look to their principles of modular design, their sophisticated wood preservation, and their deep commitment to material reuse? We might just find the blueprint for a more sustainable future, one that builds for the centuries, not just for the decade. The true legacy of the Roman carpenter is not locked away in a museum. It is a quiet invitation to look closer, to see that the most profound secrets of strength and endurance are often hidden in plain sight, waiting for us in the wood grain of history.